Picture a simple rectangular wire loop suspended perfectly still in a dark void. Surrounding it, pointing in one direction, is a uniform invisible magnetic field. The moment we send an electric surge through that wire, the loop jerks. It abruptly twists into a specific alignment with that invisible field. Notice what is missing from this system. There is no iron inside this wire. There are no permanent magnets attached to the frame. Yet it behaves exactly as if it has a north and a south pole. The physical rotation we just saw proves a core rule of physics. The moving charges inside the wire create their own magnetic identity. We call this a magnetic dipole. It is simply any object or system that has two opposite magnetic poles, exactly like a standard compass needle. To understand why that twist happens, we look back to 1820. A Danish physicist named Hans Christian Ørsted was performing a lecture demonstration. During his experiment, Ørsted noticed a specific reaction. Whenever he ran a current through a straight wire, the needle on a nearby magnetic compass deflected. The needle aligned itself tangentially, forming a perfect right angle to the wire. Ørsted deduced that the moving charges inside the wire were actively producing a magnetic field in the surrounding empty space. If you map that field, it forms concentric circles radiating outward, with the wire sitting directly in the center. When we observe our twisting rectangular loop, we are seeing the direct result of Ørsted's discovery. The twisting force on our shape is the physical consequence of those concentric magnetic fields interacting with the larger external field in the room. Here is a top-down diagram of our rectangular wire loop, labeled A, B, C, and D. It is sitting completely flat inside a uniform magnetic field, labeled B, and the field lines are running parallel to the plane of the loop. Top arm AD and bottom arm BC are sitting parallel and anti-parallel to the magnetic field lines. Because they perfectly align with the flow of the field, the magnetic force exerted on these specific sections is exactly zero. Arm AB cuts completely perpendicular to the field. This generates a force on the wire, which we will call F1. Based on the rules of electromagnetism, F1 points straight down, pushing that side of the loop directly into the screen. Over on arm CD, the current is flowing the opposite direction. This creates a second force, F2. It has the exact same magnitude as F1, but it acts in reverse, pushing directly out toward us. You have one side pushing straight down and the other side pulling straight up. Because these two forces are physically separated by the width of the loop, they form what engineers call a couple. This separation creates torque. Torque is the rotational equivalent of linear force, measured by multiplying the force by its distance from the pivot point. The loop rotates because its rectangular geometry splits the magnetic interactions into a rigid push and a rigid pull on opposite sides. To calculate exactly how hard this loop will twist, physicists use an area vector, denoted by a capital A. You find its direction using the right-hand thumb rule. Curl the fingers of your right hand in the direction the current flows, and your thumb points perfectly straight along the area vector. This brings us to the magnetic moment, represented by a lowercase m. You calculate it by multiplying the current I by the loop's area, A. This single value defines the overall magnetic strength of our loop. If you wrap the wire into a tightly wound quill with multiple turns, represented by a capital N, the magnetic moment scales up. You just multiply the original equation by N to get the new total strength. Now we have our final mathematical picture. The torque, the Greek letter tau, equals the vector cross product of the magnetic moment m and the external magnetic field B. The cross product is a mathematical operation that takes two vectors and produces a third vector that is perpendicular to both of them. If you study electricity, this looks highly familiar. It is the exact mathematical twin of the equation for an electric dipole in an electric field. The math confirms that electricity and magnetism operate on the exact same underlying logic. Subjected to this torque, our wire loop rotates toward a state of stable equilibrium. It turns until its internal magnetic moment strictly aligns parallel with the external magnetic field lines and comes to a dead stop. In this exact orientation, the perpendicular distances that created our push and pull vanish entirely. The torque drops to zero. Simultaneously, the maximum possible amount of the magnetic field is now passing directly through the open window of the loop, a state known as maximum magnetic flux. If you swap the wire loop for a solid iron bar magnet, the mechanics do not change. The magnet will twist itself until its north pole points perfectly along the surrounding field. Whether we are observing a simple circuit on a lab bench or the massive magnetic fields generated by a planet, the mechanism holds. Moving charges dictate the physical orientation of objects, exerting a precise torque until they find their stable alignment within the field.